Today we're going to be talking about maximum entropy modeling. Just to give you a roadmap about what we're talking about today, we're first going to talk about a motivation for why we need a more powerful probabilistic modeling formalism. We'll be working with the example of doing part-of-speech tagging. And along the way, we'll have to introduce some key concepts from information theory and optimization in order to talk about the main event, which is maximum entropy models, how they're formulated and how they're learned from data. Okay, so first, the motivation, supervised part-of-speech tagging. A large part of this course is talking about how to model distributions and estimating them from data, and thus far, the approaches that we've talked about have only involved counting, and sometimes we're counting in very complicated ways, using priors and backoff, but we're still only counting discrete objects. But what if we know something about the features of the things that we're trying to model? That gives us some notion of similarity or dissimilarity. This is a common task called supervised learning, where you have some annotated data, you build a model, and you apply it to unseen data. And so let's take a look at part-of-speech tagging, where the annotations are words with part-of-speech tags. We build a model using some feature representation, and then we apply part-of-speech tags to some unlabeled sentences. And so in the past, we talked about using hidden Markov models for this task, and they're quite simple and easy. They only have three parameters: this initial distribution, a transition distribution, and a conditional distribution. And it's very easy to get these parameters from tag data and then to find the best sequence using Viterbi. But one thing we'll see is that these models don't always capture all of the insights that one might actually use to do part-of-speech tagging. And if we figure out a formalism that does incorporate these insights, we might have a better model. So for example, let's say that we're trying to tag a sequence of words W with some tags T. One thing you might notice is that if you have a modal tag in one of your previous tags, then the base form verb is more likely than an inflected form of the verb. Similarly, if one of the tags that come after is an adjective, then a comparative adverb is more likely than a comparative adjective. And if one of the previous words is not, then a base form verb is more likely than an inflected form of the verb. And we can also look at properties of the word such as subsequences of characters within the word. So for example, if a word ends in the character sequence tion, then it's more likely a noun, but if it ends in ly, then it's more likely an adverb. And so if we're able to represent our data using features, this becomes a lot more powerful and expressive than counting single observations. And so we'll represent this by a vector f. When applied to an observation x, and we will talk about individual elements in that vector with the subscript. And so a typical example is that if we want to encode whether a particular word combines with a particular tab, we have a Boolean feature that is 1 if this word is present and this tag is in the sequence. And 0 otherwise. And so these feature vectors can be quite long. Okay, so suppose that we have some data, and this gives us some information about the features. What distribution would we use to model these features and observations? And so this is where the concept of maximum entropy comes in. But before we can talk about that, we need to make a detour through information theory and talk about entropies and expectations. Okay, so an expectation is just defined as the weighted average based on the probabilities. So if you're taking an expectation of a function over some event space x, you take a look at all of the elements in x, and you multiply the probability of that outcome by the value of the function at that outcome. And this is true for discrete or continuous probability distributions, but because this is natural language processing, we'll mostly be working with discrete spaces. And expectations of things that are constant, that is not probabilistic, are very simple. It's just that value. Similarly, if you condition on something, that's equivalent to being a constant. What is the expected value if you roll the die of the number that will come up? So you take all the numbers and you weight them by their probability. So the probability of each of the outcomes is 1/6. You weight those, and you get 3.5. How about for 2 dice, if you roll them together? So here the probabilities aren't uniform anymore, and so we can take all of the outcomes going from 1 to 12 and weight them by their probability, and we get the answer 7, which also shows you that expectations are linear. The other concept that we'll need is entropy. So entropy is a measure of the disorder in a system. It comes from physics, developed by Ludwig Boltzmann here on the right. And it can also be applied to probabilities. So you have some distribution, and if in that distribution only a few outcomes are likely, you have low entropy. But if things are more equiprobable, if things are more chaotic, you have high entropy. So this does not account for the values of the random variable, only the spread of the distribution. And so uniform distributions have the highest entropy, and point mass distributions have the lowest entropy. And entropies are always going to be greater than or equal to 0. So what's the entropy of a roll of a die? So in this case, it's just 1/6 times log of 1/6, added together 6 times, and then you take the negative of that, and that gives you 2.58. How about a roll of 2 die? And so this is a little trickier question. Will it be higher or lower than the first one? Initially, you might think that it should be lower entropy because 2 die have a non-uniform distribution, but there are more outcomes in this event space, and so you actually get a higher entropy because you have more outcomes. And so the maximum entropy principle says that all else being equal, you should prefer distributions that maximize the entropy, because that basically says that you should not assume that you know more than you do. And if you don't have evidence to say that one thing should be more likely than the other, they should be equiprobable, and entropy incorporates that intuition. But if we just use this principle, then the only distribution we would model is a uniform distribution. But we know more than that, so how do we constrain our distribution to match what we know from the data? And then the other question we need to answer is how mathematically do we optimize the entropy? Okay, so now let's talk about adding constraints that reflect what we know about our data. So one obvious constraint is that our distribution should be a probability distribution. That is, it should sum to 1 and be non-negative. Okay, so how do we incorporate features into this modeling? We observe features across many different outcomes, and we're modeling a distribution over these outcomes. And so what's the correct model of features under this distribution? And now, one of our big motivations is that we don't want to count the outcomes. We've discussed those methods, so let's leave them aside. And so what we're going to say is that we want the estimated counts under our distribution, P, that we're trying to model, to match the empirical counts. So we take a look at all of our observations, and we compute the empirical expected counts of those features. And whatever we're going to model our distribution P as, it should match the empirical counts. Now we need to take another mathematical detour and talk about how we optimize constrained functions. And so the way that we're going to do this is use Lagrange multipliers. And so given functions f and g, The critical points of f, restricted to the set g equals to 0, are where the gradient of x equals the gradient of g times some multiplier lambda that's called a Lagrange multiplier for all of your different variables that define your function, and also where g is equal to 0. So this gives us a set of n+1 simultaneous equations over the n+1 variables x1 through n, all of the variables that define your functions, and this new parameter lambda. So let's take a look at an example. Let's say that you want to optimize a function, the square root of x times y, subject to the constraint that 20x plus 10y is equal to 200. So first you compute some derivatives, and now we form a system of simultaneous equations based on what we talked about a second ago. So we differentiate f and g with respect to x and y. That gives us two separate equations, and then we have a third equation based on our constraint. And so now we have three equations, and we'll use algebra to solve them. And when we do, dividing the first equation by the second gives us y over x equals 2, and plugging that in gives us x is 5 and y is 10. Okay, so now we know how to optimize functions, so let's form an objective function that gives us the maximum entropy model of this distribution. Okay, so we want to find some distribution P that maximizes the entropy, as defined here, under the constraints that it is indeed a distribution, and that for this distribution P that we're trying to discover, the expectation of the feature under P matches the empirical expected value of the feature. So we set up our Lagrange multipliers, like so, and this gives us the functional form of our solution. We'll walk through the actual solution in class, but what you get is something of the form that the probability of an observation x is proportional to the x of lambda times the feature vector, where lambda is a vector of real numbers of length equal to the number of features you have. And each lambda tells you how important this feature is. If one element of lambda is positive, that means that seeing this feature increases the probability. If some lambda is negative, that seeing this feature decreases the probability. And so now we have a distribution defined in terms of these features. But then how do we learn this lambda? While there are many algorithms for discovering this lambda, the ones that we'll talk about all take the same iterative form. You first start with lambda equals to 0. You basically know nothing about which features are important, and then you determine an update in terms of some displacement vector delta, and then you add that to your current guess of lambda, and you keep doing that until the lambda stop changing. So what we're going to do is we're going to maximize our objective function, which is just the probability, or the log probability, of our observations x. And we have a lot of them. And so basically what we're going to do is we're going to take the gradient and walk up the gradient. And if you look at what the gradient actually looks like, it's basically saying that we want our current expected feature values, the first term in equation 10, to match the empirical feature observations, the second term in equation 10. And so if they match, then we don't change that entry in lambda. Otherwise, we increase it or decrease it as needed in order to make the expectations match. So this becomes our delta, but with a scalar alpha. And we choose the alpha that gives us the maximum likelihood using some sort of grid search. And there are other parameter estimation techniques for lambda that are talked about in the book, such as iterative scaling and conjugate gradient methods. Because this is a convex optimization, the real difference is speed and scalability. One advanced concept that I wanted to talk about very briefly is that typically we want to prefer smaller values of lambda over larger values of lambda. To encourage this, we often use a form of regularization to penalize overly large values of lambda. And this is equivalent to having a Gaussian prior over the weights lambda. It's also possible to use informed priors if you have an idea about which features are more important. This is also used for domain adaptation. And I want to stress that this isn't just for joint distributions. It can also be for conditional distributions. It just is a matter of how you define your features. MaxEnt distributions have been a workhorse of natural language processing and computational linguistics for decades. They've been used for part-of-speech taggings, for supervised classification, for parsing, because it allows you to specify features such that you get a better model of the underlying distribution. And in class, we'll talk a little bit more about these applications and also give some idea about how you actually construct features for particular problems. We'll also have a quiz as usual, derive the MaxEnt formula, and talk about the results for the language modeling homework.